And actually, quick update on chapter 9. Let's quickly go back to that handout. Okay, so chapter 9, we briefly talked about J-values, right? J-values, again, they're just the little distances between the peaks within one signal. Now, I told you guys to just memorize those values, right? Now, that was usually very helpful like a couple of semesters ago. Now, usually for the past 2 semesters, he's been focusing a lot more on the Karplus curve, and that's something that I forgot to really mention to you guys. I told you that it was just the conceptual stuff, which is true. Yeah, it's just the conceptual stuff. Now, technically, he's always going to give you some sort of chair, and he's going to tell you HA, HB, or HC, for example. Something like this. Now, in this case, sometimes he's not going to follow the exact ranges that we did here. He's going to base it on the Karplus curve, and that's why he was showing you guys that in lecture. Specifically, he was pointing out to 3 specific angles, which are basically 0 degrees angles, which is going to correlate to 8 hertz approximately. Then we have a 90, which is going to be less than 1, and then 180, which is like right at 10 hertz. Now, I would try to memorize like those 3 key values and remember how that the Karplus curve looks like to figure out the approximate J value, the approximate hertz value. Okay, so just keep a note of that. Again, if you're confused with this, don't worry too much about it because it's just going to be 1 question probably, max 2 questions, but focus on the other stuff because that's going to be worth more points. Because if most students get the question wrong, he's going to curve it. Exactly. So everyone get it out. No, but give it a try. The values. So yeah, it's going to be like, if the angles, the dihedral angle, it's 0, if it's 90, and if it's 180, like those are the 3 main ones.
But then what did he also say about uplink, like when it's like 12 to 15? I don't know.
Exactly. There are some values that technically are not touching the Karplus curve. So that's why like figuring out the exact hertz value, it's kind of complicated. And there's more behind it, but for this class, he's not really going to test you that deep. So again, if you get confused, don't worry. It's just 1 question. Focus on the other ones that are going to be harder. Yes. No. You don't need to memorize the entire story. I just say that so it's helpful for you guys. And also like in lab, you're going to see it quite often. So that's for mostly lab. But for this class, like IR is just going to be little baby hints that he's going to give you. Mostly it's going to be based on HNMR. So if you don't know anything about IR, you should be good as long as you know HNMR. And that's it. Okay, so now let's go back to the actual handout for chapter 11 and 12. Okay. Okay, so last session we were talking about those 3 reactions: addition reactions, elimination reactions, reactivity of carbonyls, and we started talking about what exactly is oxidation and reduction, right? Now, for the first exam, it's going to be mostly focused on the reduction aspect. Really quickly, what's reduction? Adding bonds to oxygen.
Reduction is breaking a ion and losing
Basically, yes, you're decreasing the amount of bonds between carbon to oxygen. Oxidation is increasing the amount of bonds between oxygen to carbon. So please remember that. Oxidation is when we go from an alcohol to a carbonyl. Reduction, when we go from a carbonyl to an alcohol group. Okay, now let's talk about the first 2 reductions, which are with the sodium and the lithium reagents that he did in class today, actually. Now, how many of you were following along while he was explaining those things? With it? Okay, that's good. How many of you were really confused? Okay, we have like a good chunk. Okay, so let's quickly talk about this. Before we fill that out, let's just look at the reaction. Okay, so first of all, you have to identify what's going to be your electrophile and your nucleophile for each of the reactions that we're going to do. Now, in this case, the carbonyl group, we were talking about its reactivity, and we were saying how it's easier to attack aldehydes, right? So since we're going to be attacking that aldehyde or any carbonyls, the carbonyls are going to be the electrophile for this chapter. So this is going to be your electrophile. And more specifically, the part that's going to get attacked is gonna be this carbon over here. Why? Because we have a little dipole moment there. So that carbon is gonna have a delta positive, making it electrophilic, and the oxygen delta negative. Okay, now, next part is gonna be the hydrogen from the reducing species that you have. In this case, it's highlighted in red. That's gonna be the important part. Again, this should be the nucleophile specifically. And then what you see at the bottom is just, it's gonna be any sort of solvents. It can be water, it can be that acid, it doesn't matter. We only needed to do a last protonation step and that's it. It's not really that relevant.
Protonating the negative oxygen, correct?
You got it. Okay. So again, what was the nucleophilic species for reductions? Specifically, what's the nucleophilic part? The hydrogen, exactly. It's going to be the hydride ion. So it's going to be that hydrogen with that lone pair that has a negative charge. That's going to be the actual like nucleophilic species. Now, like we've seen, like in many reactions at this point, the nucleophile is just going to attack the electrophile. And remember, whenever nucleophiles do that attack, they are connecting themselves to that position. So in here, I'm just attacking that carbon, and to not break the octet, I have to kick up the electrons towards the oxygen. So now I have that little hydrogen from the reducing species, and I still have that oxygen, but this time everything is in a single bond. So far, questions on what we just did? Okay, now, something else that you guys should notice is that we're going from an sp2 carbon to an sp3 carbon. We're changing the stereochemistry. So it's important to notice that, because a conceptual question that I've seen him ask is, what's going to happen after the nucleophilic attack whenever you use either the sodium reagent or the lithium reagent? And it's going to be the transformation from an sp2 to an sp3 carbon. So just keep that in mind, just in case. Okay.
So whenever, even if we use the lithium aluminum one, it still goes from SP2 to
It always goes sp2 to sp3.
SP3.
That's on the first step. When you do the nucleophilic attack, yes. Yes.
Oh, question. He did one where he had a cyclic ester and he called it a lactone.
Yes.
How does it break, I guess?
We're going to be talking about those right now because we're only talking about the weak reducing agent. Remember, that's only going to be able to react with the most reactive carbonyls. Lithium is going to be the one reacting with the other ones. Okay. So after that, we can see that everything is pretty much stable. The only thing that we have to neutralize is that oxygen, right? So that's going to be when the solvent comes into play, which was H3O+, right? So it's just going to be a simple acid-base reaction. Lone pairs just attack that hydrogen, and then you're able to create this guy. Whoops, that's not the correct answer. Let me rewrite this. You have your hydrogen. And we have hydrogen. And there we go. Okay, so we have the hydrogen. That one was from the acid. Remember that, because in this case, remember, the only reason why I'm showing you the mechanism is because he's going to give you isotopes. And he actually did at the very last part, I think, of the lecture, like NABD4 or something like that. Exactly. So keep that in mind. And then, okay. Remember that hydrogen, it came from the reducing species itself. Okay, so that's for aldehydes. Do we think there's going to be something different for the reduction of ketones? Or is negative? Yeah, exactly. It's pretty much the same thing, same mechanism. So can someone just walk me through the mechanism really quickly, step by step?
All right, so you're gonna break that pylon.
How?
The H is gonna attack the partial positive.
Mhm.
So then it becomes, it adds to that carbon, and then you're left with the O with the negative charge. And then from the other part of the solution, the hydronium adds another H.
So yeah, pretty much nucleophilic attack, acid-base reaction. That's it. Pretty simple reduction for this one. So let's just write OH and then hydrogen. And again, remember that hydrogen, it came from the reducing species. And then the one that protonates the alcohol is from the acid or solvent that you have at the beer bottom. Yes. So if he gives you isotope, like the only isotopes that he's gonna give you so far is just with hydrogens. So like the main structure of the reagent is gonna look the same, and the only difference is gonna be that, for example, if it was, oops, that's the wrong one. NaBd4, for example, in this case, it would be a deuterium with a negative charge doing the attack. And then at the very end, you would have your alcohol group, and you would have a deuterium right there instead of a hydrogen. That's it. Yes.
What about when you're, I guess so when you have the nucleophile, it attacks the hydronium, but what if that instead of hydronium, it's like a compound with like a bunch of C's, like another.
So remember that the compound is, the actual reagent is gonna have an ionic bond, which at the end, we know sodium is gonna be just floating around, and the
Right.
main part is gonna be the boron with those 4 hydrogens. At the end, the only thing that's gonna do the actual attack is gonna be the hydrogen, because boron is gonna be happier with only 3 bonds. So something else is gonna happen to make one of those hydrogens leave. So boron can be stable.
At the end of class, he was talking about how these reactions, but kind of like a tail to it, like more stuff, and then it gets added to the molecule you're manipulating.
That's for Grignards. We're getting
Right,
ahead of
okay.
ourselves. Yes. But so far, we're just talking about hydrogens. Hydrogens are getting added. That's it. Yes. In this case, we went from sp3 to sp3 still. We're retaining that configuration basically. Okay. So technically, you don't really have to do the full mechanism. What you're gonna see, it's a pattern for aldehydes and ketones. So that's when we go back to this part of the handout. You just add hydrogen, exactly, yes. Exactly, just you add a hydrogen. Now, your aldehydes are always gonna end up as primary or secondary alcohols. What did we find out?
No way.
Primary, exactly.
Oh, because it's the H.
Mm-hmm. That's what we got here. This is a primary alcohol. What about the ketone one? Primary or secondary? Secondary, exactly. So that's always going to be a pattern that you're going to see for reductions with the sodium reagent, okay? Aldehydes, they always get converted to primary alcohols. Ketones always to secondary alcohols. Okay, so far, questions on those 2 reactions? Yes. Yes. Yeah, it's going to be the same way because at the end, the main nucleophilic species for both of them is going to be that hydrogen. Mhm.
Is he gonna give us ketone aldehyde with one or is it do it?
He usually just gives them with the one with sodium. I haven't seen him do the one with lithium. Yeah, because remember, aldehydes and ketones are so reactive. They're going to be so easily attacked. Yes. As long as it's protic, yeah. As long as it can give a hydrogen, it's good. Yeah, in this case, it's not really going to be relevant. That the solvent is only going to matter for Grignards, but we're not talking about that one yet. Okay, now let's get to the lactones part of the chapter. Okay. So first of all, notice how on the aldehydes and ketones, we only had 2 main steps, right? Nucleophilic attack, acid-base reaction. Now, what you have to keep in mind is that aldehydes and ketones do not have any leaving groups. But whenever we're talking about esters and carboxylic acids, we are going to have leaving groups. And your leaving groups in this case are always going to be highlighted in purple. It's going to be that oxygen connected either to a hydrogen or some sort of carbon chain. Now, the reactions are going to start the same way. Now, in this case, remember, those 2 guys are only going to react with the lithium reagent. Why? What was the reasoning behind that?
Lithium stronger.
But why do I have to use the stronger one? Because they're less reactive, exactly. They're bulkier, exactly. So it's going to be slightly harder to attack them. So we need something that's stronger.
Right, that those 2 are esters, both
ester, and that one's the carboxylic acid. Okay, so same process, everything starts the same way with that hydride ion. So that hydrogen, again, that's the one that came from the lithium reagent. It's doing the first nucleophilic attack to the carbon. And again, to not break the oxide, push up the electrons to the oxygen. So now we have the O minus, and we have our hydrogen from exactly the little baby hydrogen. And then once we have that, with ketones and aldehydes, we saw that it was just an acid-base reaction, right? But in this case, because we have that leaving group, we're not going to be doing that quite yet. What's going to happen is going to be that you're going to gain back the sp2 configuration. How? The lone pairs in that oxygen are going to go back down to reform the double bond, and that's going to kick out your leaving group. So once you do that, what kind of functional group is going to be created? Ketone or aldehyde? It's going to be an aldehyde, exactly. We have that reformed double bond. We have the hydrogen from the nucleophilic attack. And then we have our little byproduct, which is just an alkoxide. Okay, now, what do you think is going to happen next? Is that going to be my answer?
No, then the H3O plus is gonna protonate.
Okay, it's going to protonate the oxygen. And so I'm going to have an alcohol and an aldehyde as my products.
No, I think the chains are gonna combine together.
The chains are going to combine together. What do we think? What's going to happen at this point? What was the main purpose of a reduction? Yes.
First one on the left to, double.
Exactly. So yes, remember the whole point of reduction is to remove the amount of bonds between carbon to oxygen. So I don't want any carbonyls to be there. I just want pure alcohol groups. That's going to be the simplest product that I could have. So in this case, you're going to assume that you have excess of the lithium reagent. So that means that, again, that hydride ion is going to come back and it's going to do the same thing. Nucleophilic attack, and then that's when we get that sp3 configuration again. So we have for O minus, we have the hydrogen from the first attack, hydrogen from the second attack, and we still have our little byproduct. What else is going to happen? What's the last step? Exactly. We're just going to neutralize everything with a simple acid-base reaction. In this case, we have H3O plus as our solvent. So that's going to come back again. And remember, both oxygens are just going to be attacking the acid. And that's it. You end up with 2 alcohols in this case. And then those hydrogens are still there. Okay. Yes.
So after the reaction, you can put the base.
It's going to be those 2, yes, but he's only going to be asking for the major one in this case. The leaving groups are going to be considered the minor products. So in this case, the one on the left, that's the one that you actually care about. Okay. So, yes.
The H3O only comes in at the end when it's protonating, O minus, correct?
Yes,
Other than that, we're gaining the hydrogen from the liquid.
exactly. Yes. Yes. Basically, what are we doing this up? Is that your question? So remember, the goal of reductions is to reduce the amount of carbonyl groups that you have. So to do that, we have to repeat the process. And that's always going to be, I'm sorry? You have to reduce everything percentage because we have a reduction, a reductive species there. So that's why we have to go all the way to the alcohol groups, always. Question? Technically, no, but an intermediate that you should know is that this is just a general term. This is just a tetrahedral intermediate. Neutral intermediate. It's not really that relevant. It's just in case. I know that that one is going to come up probably for the next few chapters, but for now, I wouldn't worry about that one too much.
Is that because of the shape of the?
It's because it's an sp3 carbon at the end. So now it's going to be a tetrahedral in the geometry. Okay. In this case, yes, because we're dealing with leaving groups in this case, just because of that reason. Okay. Next one. He mentioned the name lactones, right? What are lactones?
Aromatic ring ester,
Aromatic ring with an ester.
or ring cyclic ester.
It's a cyclic ester. Yes, thank you. So yes, we're gonna be talking in another chapter like how to actually name them, but so far, this is just a lactone or a cyclic ester. Cyclic ester. Now, same process. We're still doing a reduction. The only difference is that this time everything is cyclic. So you have to keep that in mind. Okay, so that hydrogen ion from the reducing species is just gonna do the nucleophilic attack. And we're gonna have our tetrahedral intermediate. So we have, oops, this molecule, O minus, and remember that hydrogen got added there. What's gonna happen now?
Double bond.
Okay, so lumpers go back down. Exactly, because remember, next step is just to kick out your leaving group. So in this case, that cyclic structure now is gonna be linear, and that's it. So that's when you have to keep track of your carbons. So let's just label them. This is 1, 2, 3, 4, and 5. And then let's start drawing out this structure. This is your hydrogen. Double bond, we have 1, 2, 4, and 5. And then we have an O minus over here. Okay, so far, are we following?
Now the leaving group.
Okay, good.
Now the leaving group.
The leaving group already left.
Uh,
Because at the end, whenever we're talking about like the leaving group goes away, is that we're breaking that bond between carbon and leaving group. That's it. So I'm just chopping it off. And then because it's cyclic, it's still gonna be hanging around.
Oh, and then it just keeps going, right? You added H to the O and then break that double bond, you add H to that carbon and
Exactly. Now we just have to keep reducing. Nucleophilic attack, kick up the electrons. And now you have almost the final product. We have our O minus, hydrogen, another hydrogen. And then very last step is just gonna be without H3O plus. That's gonna protonate it. And that's it. Yes. Actually, let me zoom out. There we go. Right there.
Can you recap everything we just did in that problem?
Yes.
Wait,
Okay, so in general for esters, let's just go step by step. First thing that's gonna happen is the nucleophilic attack, which means that you add that hydrogen from the reducing species. After that, we reform the double bond and kick out the leaving group. So we're just chopping off that bond between carbon and oxygen with the R group. That's it. After that, because I reformed that double bond, I need one extra hydronium ion, sorry, an extra hydride ion to do the attack. So again, I'm just attacking and I'm attaching an extra hydrogen to that carbon. After that, now I can finish off with the acid-base reaction. And that's when the solvent comes into play. Questions? Very good?
basically only 2, 3 items that we have.
Kind of,
What,
but let's keep going with the handout. Let's keep talking about this. Okay,
So far, what reactions did we do?
before the addition reactions and elimination reactions.
So that was review though.
That was a review though, yeah. These are gonna be these are your first real reactions from Morgo 2.
But that's gonna be on the exam.
Yes, reductions are on your exam. Okay, now, next thing we have carboxylic acid. What do we think is gonna happen in here?
Absolutely no.
Nothing?
Leaving group. You could have to leave group. Yeah.
Exactly, same exact process. So nucleophilic attack, reform the double bond, kick out the leaving group.
The lead would be,
Oh, no.
waste this time.
Mm-hmm. Yes, so your byproduct technically is gonna be water.
Well, I get it, the 5.
Yeah,
Yeah.
it's a byproduct. Okay, so do you guys need me to show you the mechanism for that one? Yes, okay, let's go through the mechanism really quickly. Okay, so again, first step, just the nucleophilic attack. So I have my O minus, and I have my hydrogen. And my leaving group is over here. Now, this is the point where I reform the double bond, and I kick out my leaving group. So now I have an aldehyde plus OH minus, which is my byproduct at this point. Questions so far? Oh, what just happened? Okay, let's go back. Let's go back, everyone. Okay, that's the pointer. Okay, so remember, first step is just that hydrogen from the reducing species comes into play, attacks there the carbon, so it's gonna get attached there. Do not break the octet. Electrons have to go up to the oxygen. So that's how we form the tetrahedral intermediate. It's the same structure, but I just added that extra hydrogen, right? Now, because I have that leaving group, that OH group, I have to reform the double bond. How? Those lone pairs in that oxygen are gonna go back down, reform the double bond, and that's gonna kick out the leaving group. So that's why we have OH minus in here, okay? And that's your byproduct. Okay, after that, what's gonna happen now? This is when I do my acid-base reaction?
No, just when you break the 5 on, allowing for, oxygen.
Exactly, so that hydrogen is gonna come again, do the nucleophilic attack. So we form again the tetrahedral intermediate. So we have O minus, the hydrogen from the first attack, the hydrogen from the second attack, and we still have our byproduct. So now, very last step is just your acid-base reaction.
You still reduce when you have a double, you could only reduce when you have a double bond.
Only on a 5 on. You can't
Only at a
reduce
pi bond, yeah. So we have that
it.
alcohol,
So H2O is base.
acid, yes, because it's the one getting attacked. And we have H2O as your byproduct. Okay. Questions?
That's getting attacked.
The acid is the one getting attacked. Yeah. Bases do the attack, acids get attacked. Okay, now, again, I just showed you the mechanism so you can follow around where the isotopes would go, right? So a shortcut is gonna be shown in here. Okay, simple as that.
Going
So on the left side, we have our aldehydes and ketones.
Can you like,
So we have a ketone and an aldehyde, right? So those guys are so reactive, they're gonna work with the sodium reagent and the lithium reagent. And aldehydes are always going to a primary alcohol. Ketones are always going to a secondary alcohol. And then if you have an ester or carboxylic acid, they're gonna need a really strong reducing agent, and they're both gonna end up forming the same product, a primary alcohol.
see the answer, sorry.
This part? Or like, do you want to? I'm talking about the shortcuts basically for the reactions that we did. The left one is ketones and aldehydes. The right one is your esters and carboxylic acids. It's the same thing that we just went through, but basically just summarize, and that's it. Yes. No. You're always going to be expected to assume that you have excess of it. Yes.
Is he gonna ask simple questions, like, could we literally, use the shortcut, or he's gonna
Yeah.
add stuff to the,
The only complicated stuff with reductions like this is the isotopes, and that's it.
what's in the brain, right?
And the rings, technically, yes. So for the rings, just keep track of your carbons, count them, and that's it. The very last thing is just filling this part out. So it should be pretty simple at this point. Esters are gonna go to, are gonna form what? Primary or secondary alcohols? No,
Primary.
primary. What about carboxylic acids?
Right.
Primary as well. And it was in the shortcut that we just saw as well. Mm-hmm. Okay, so far, any other questions? Okay, no. We're gonna skip the problems in here. It's basically just to test you what kind of reagent you have to use. If we don't get time on Friday to do them, I'm just gonna post the answer key on Friday, so don't worry about that. But I wanna do this one before we talk about Grignards. Okay. So in this case, remember, everything is gonna be in condensed formula for the exam. So you have to get used to this format. Okay, so which reagent would we use to perform that transformation? No clue.
So you wanna use A because if you use B, it's gonna reduce that ester that's in the middle.
Oh,
That's
the CO2,
right.
the CO2 is bonded
Yeah.
to the CH3, which is the ester, but it
Yeah.
doesn't change.
Exactly.
your
In this case, you have two carbonyls. So the most obvious one was the ketone in here. Now, what usually most students tend to forget is the little ester that's over here. Remember, whenever you see a carbon right next to an oxygen, that usually means the presence of some sort of carbonyl group, okay? So keep that in mind. And in this case, we can see that the ketone, now it's a secondary alcohol, right? And then the ester, it's still an ester. So it makes sense that we have to use only the weak one so that ester is not affected. So that's why A is the answer. Questions on that one? Yes. So what would happen if the ester would have actually like gone to an alcohol group or the lithium, then we would end up with two alcohol groups because the lithium one is going to be able to reduce that ester. Okay. Okay. Grignards. You see the dog? XM1. Keep that in mind. Now, Grignards, it's a reduction reaction, so it should be pretty similar. There's only going to be something special that we have to talk about. But first of all, really quickly, before we look at anything in the handout, what's going to happen in a Grignards reaction? Does it have special rules?
Mg,
Halogen.
We have some sort of halogen. What else? What do we remember?
Alkyl,
air, and then arrow.
Aryl.
vanilla.
Yes.
Yes.
We're just naming
Attached to,
positions.
Magnesium.
Magnesium
And it has
and a halogen in the back. The carbon chain, exactly. Okay, now, Grignards. Before we actually get into the reaction, let's talk about some conceptual stuff. So, remember how in the previous reductions we're doing a nucleophilic attack, right? Now, first of all, what's the difference between nucleophiles and bases?
the nucleophile is the electron donor, and then the base would just be like the weak base.
No, a nucleophile is an electron,
They're the
it
same
wants,
thing.
it wants nucleus, wants.
The same thing? Okay, let's start with the easiest one. What do they have in common? What's the similarity?
Both want to.
They're both negative charges.
Oh, yeah.
Both have negative charges and they're both going to be attacking something. Exactly. So that's gonna be here, so negative charges, and they attack. Now, the difference is that, remember, bases are gonna be taking away some sort of hydrogen. So they're breaking a bond technically. Now, nucleophiles, like we saw, they get attached to the molecule. So they're making new bonds. That's the main difference. So nucleophiles make new bonds. And then bases, they take a hydrogen. Simple as that. Now, the Grignard reagent, let's see how it looks like first. So we mentioned magnesium and some sort of halogen, right? Now, usually for the reagent, it's going to be magnesium with bromine. That's most of the time, but it can be any halogens. Now, the actual Grignard reagent, the one that's going to be doing the attack, remember, it has to be a nucleophilic species, so we need some sort of negative charge and that lone pair. So what's going to happen is that MGBR is technically going to act as a leaving group or an ionic bond. So at the end, we're only going to be having a carbon chain. And since we're breaking that bond, the lone pairs, sorry, the electrons are going to that carbon. So that's why we have those lone pairs in there. And now we have a negative charge, a carbon ion. That's going to be the nucleophilic species for Grignards. Okay. So far, questions on that? We're good? We're good. Okay.
Where did the MG and the VR go?
They're technically just
Floating.
floating around, yeah.
Okay.
Yeah. Expected writings, yeah, we don't care about them. Okay. So just by looking at that Grignard reagent, what are they going to be? Like strong nucleophiles, strong bases, or maybe both? Do you agree?
You repeat that?
What are going to be Grignard reagents? Strong nucleophiles, bases, or both? They're going to be both. They're going to be considered strong bases, and
Because you're gonna take
because if they take an H, that carbon is going to become neutral. That carbon is going to fulfill those 4 bonds that it needs. So in this case, let's just say both. Okay, so for the previous reductions, the one with sodium and the one with lithium, there was nothing really that special. We didn't have any rules or exceptions, right? Now, in this case, because Grignard's is both a nucleophile and a base, we have to be more careful on what we have in the molecule. Why? Because Grignard's can act as the base if you have anything acidic in the molecule. So you have to keep that in mind. So let's just write here, whenever there's an acidic proton.
How do we know that proton?
Alcohols. Those are going to be usually the only samples you're going to see, alcohol groups. Now, with the lithium reagent, we were able to reduce a carboxylic acid, right? But carboxylic acids are very acidic, so they're not going to work with Grignard's. So that's where the photo comes into play. The carboxylic acid, it's the little baby duck. So it's away. So it's not with a Grignard reagent, so it's not going to react with that one. Okay, that's why I put that photo. Question in the back? Okay, we were just stretching. That's good. Okay, so before we actually see the attack of the reduction, you guys have to know how to make the Grignard reagent. So that's going to be only like 3 main parts. First of all, you need some sort of alkyl halide. So that means a carbon chain with some sort of halogen. Usually it's just bromine, but it can be chlorine or any other one. Okay, doesn't matter. And then as your reagent, you need magnesium, of course, and then ether specifically. What ether? What kind of solvent is it?
Polar.
Polar
How do-
A product.
Is it because it's like almost neutral overall?
Exactly. The whole molecule at the end is going to be neutral. So that means that it's going to be an inert solvent. It's not going to be that reactive. Inert. An inert solvent. It's not going to be reactive, so it's not going to be interfering with anything. Because remember, Grignard's is very special. If we have anything acidic, the reaction is not going to happen. That's why it has to be ether usually. So that's how we form our actual Grignard reagents. That magnesium just gets in between bromine and carbon. And we know that to get the actual nucleophilic species, we cross that out and we end up with the carbon chain, the carbon ion. Okay, so far, any conceptual questions on Grignard?
We don't need to know the mechanism of how to make it. It's just
Identify the main parts that you need. Alkyl halide, magnesium, ether.
But not like, oh, the magnesium, bromine.
It's just expected of you guys to just memorize that part, but he's not gonna ask you, show me the curved error mechanism for this.
You
No.
do energy.
Yes. So yes, again, very important part. When Grignard acts as a base, it's gonna be whenever you have any acidic protons. Anything that's acidic, usually it's just gonna be an alcohol group. So carboxylic acids, like we saw here with the little baby duck, those are not gonna work with Grignards. Okay,
But it will work, it'll just act as a base.
it's gonna act as a base, yes.
And we don't-
We don't want that. We wanna use Grignards for an actual reduction and not as a base. Okay, any other questions? Yes.
The ether, how does it come into play? Like, why do we?
The ether is just basically the liquid around.
Okay.
So we need some sort of solvent that's around, that's not gonna be touching, that is not gonna be messing up with the actual Grignard reagent. Okay. Are we ready to see the mechanism this time? Okay, let's do it. Now, it's gonna be the same process technically. We're gonna start easy with a little ketone. Okay, a little baby ketone, exactly. So again, we have the dipole moment, so we have delta positive, delta negative. We're gonna be tagging delta positive, right? Now, in the previous reactions, we used the hydride ion. What are we gonna use now?
That's gonna attach.
It's
to it.
gonna, so the MGPR, like what I understand, is gonna go away, so when you have a carbocation, which will
A
extract.
carbon ion.
Carbon ion. Yes.
Anion.
Mm-hmm. So yes, beautiful. Magnesium and bromine, you're just gonna cross it out. Whatever's left, whatever carbon chain is left, just add a lone pair. And that's gonna attack. Exactly. So once we have that, now we can attack that carbon and kick up the electrons towards the oxygen. So right now we have an O minus, and we are attaching a methyl group this time. No hydrogens. We're attaching an actual carbon chain. That's the main difference between lone pair reductions and Grignard reductions.
So
Okay.
It's just a neutral state,
Mm-hmm.
because the negative charge goes away when we create that bond.
Exactly, yes. And now, very last step is gonna be an acid-base reaction. Same thing that we saw before. So H2O in this case is gonna get attacked. And you're gonna end up with this alcohol group. What kind of alcohol is it?
First year,
It,
first year.
mm, it,
It's got three.
it has 3 R groups, exactly. Whenever we're finding the degree of the alcohol, we're looking at the carbon attached to that oxygen. So yeah, this guy, it's a tertiary alcohol. Okay, so far, pretty simple mechanism, right?
Yeah.
Questions on it? It could get a little bit more complicated, yes. Yes,
So the name of that is for, you know,
this one should be. I wouldn't really use the terbutyl group because whenever we use the term terbutyl, that's whenever it's a substituent. In this case, the parent chain would be ethanol, and you would have 2 methyl groups on the first carbon. So dimethyl ethanol.
Oh.
Yes. Yes, he went over this in class. Wait, are you from Roche? How many Roche students do I have? Raise your hand. Wait. Okay, so for Roche, he already covered this. He already covered this. He's gonna start chapter 12 today. He already wrapped up chapter 11.
Thanks, I made it myself.
So this part is actually for Dr. Roche. It should be from chapter 12. Chapter 11 for Dr. Roche was mostly ethers, like epoxides, how to break them, all of that. We haven't covered that yet. In class, probably, yes. but now he's gonna be moving on to chapter 12. Chapter 12 for him, it's all about reductions and oxidations. So that's why this is new to you.
No.
But I haven't covered what he's gonna do in chapter 11, so just keep that in mind.
Where is Dr. Whitehead?
New Zealand, yeah, yeah. He didn't give you the presentation?
No.
Really? He always like makes a presentation and like shows the map and he's like, I'm from here and I studied here. And it's really cool.
I really thought.
No, he's not Australian. New Zealand. Yeah, that's why you hear the accent. Okay, we're getting distracted. We have 4 minutes left.
Do it.
We should do the second example.
Okay, the second example, it's very similar. It's technically every reduction, it's the same mechanism. The only difference is that with the sodium and lithium reagent, you're adding hydrogens. Grignards, you're adding the carbon chains.
So this we're gonna add,
Exactly. So actually, let's do a little shortcut for this one, just to see what's gonna happen.
Taking off the.
Right,
Replacing it and then replacing with that.
Okay,
kick it off, why do we kick it off?
remember, esters have a leaving group. So far, I'm drawing out the same carbon chain, but split off. Why? Because that bond is gonna get broken.
Why?
Because eventually, double bond gets reformed, and that's how the double bond, sorry, how the
esters- What? Yeah,
kicked out,
yeah,
carboxylic acids, but that was only for lithiums.
go for Grignard.
Esters, that's it. Yes. Don't worry, we're gonna do the actual mechanism on Friday because you guys should know it, but let me give you a little shortcut for Grignards over here. Let's do what happens if you have a ketone, sorry, an aldehyde, then a ketone, and then an ester. And in this case, I'm just gonna write G, which represents the carbon chain from the Grignard reagent. A little shortcut.
You don't have an S.
God, thank you. Yes. So we have that little O minus, we have H. We have OH. And then we have OH.
But what are we adding? What's our Grignard?
It's gonna be the carbon chain, so CH3, MGBR, CH3,
So we're gonna do CH.
exactly. And then let me do this, Joe. There we go. And now Grignards gets added here. I shouldn't have put that negative charge there because I'm showing you the products.
Wait, the ketone, how do you have HO? Or for all of them, why do you have HO?
Because remember, that alcohol, it comes from here.
How did we get it?
It's like what we saw here. So that oxygen, we're keeping track of it. It went to an O minus, and then
Oh,
eventually,
Brominated.
exactly. So yeah, that's a little shortcut that we have for Grignards. So you have to skip the mechanism, so you can skip the mechanism.
So just esters, there's no.
Yeah.
Well,
Lovely, yeah. Okay, so, but we're actually gonna see the mechanism Friday and whatever he covers in lecture on Friday. Okay,
Thank you.
so no problem.
That's not SI?
That's not a SI. I was thinking about it, but would you all actually like a 10?
No, I would
Yeah,
definitely.
I would definitely say that.
Like, that was like, oh, that's not even physics.
Oh, damn.
Day.
Okay. If I do a review session, which day works the best for you?
What day?
This week or next week?
Both. Which day works the best?
I would prefer next week.
Next week, Monday, Tuesday,
So it's on Wednesday, right?
Yeah.
Wednesday, yeah.
Monday and Tuesday, Monday.
Monday.
Monday?
Monday, what time? After class and elongate
What time?
that
Right after the
session.
I agree.
Right after, okay, so like 2 hours after.
So Mondays, I'm not sure if we're gonna have a room available. That's the thing. But I can do Zoom. And if it's on Zoom, I can only do it in the morning.
And then you can report.
Exactly.
Yo, can you do Monday at 4?
I don't think so. I don't think so. Probably Mondays if it works, it's gonna be Monday, but it's gonna be recorded and it's gonna be on Zoom.
That's
Okay.
fine.
So you guys have that. I'll fix up the details and I'll send you guys an email with that. So don't worry about it. No problem. Yes.
So when the apple is cut off from this side, right?
Mm-hmm.
Is the R group technically on this side or this side? Have fun.
You have
What?
two R groups.
No, that's what I'm saying. This is an R group, correct?
MGBR is not an R group. The
Okay.
ethyl is an R group.
The ethyl is the R group. So
Yes.
when you cut off the MGBR,
Mhm.
is it technically on the right side or the left side?
It doesn't matter. It really doesn't matter. As long as that ethyl, that has 1, 2, 3 carbons. It has
That's
one
what-
extra carbon.
That's, okay. So I'm
So
not retarded.
just erase it.
And,
And then, yeah,
like, well,
and that's it.
So
Mhm.
and you can get. Right there.
Did I
Where-
draw a line there?
Huh?
Did I draw a line?
yeah.
Uh-oh, you did a oops.
That's why.
I did an oopsie there.
I was like, oops.
Wait, no, I didn't do an oopsie. I didn't do the line.
Maybe I
You did the oopsie, yeah.
Thank you, Stan.
No problem. Take care.